Hello mates and welcome back. So in today's section, we are going to understand in detail about the Docker images. Now, before proceeding with any image management commands or running a further container, we need to understand first, what is the Docker image functionality, how its structure is, and how it works. Now, before proceeding further with the Docker image section, we need to understand first how an operating system is being deployed in the previous scenarios or in the alternate technologies. So if you speak about an bare metal hardware, a preferred method of deployment still is operating system or the network-based methods. Now with the advent of VMware technologies, OVA or the OVF templates or an ISO image is still a preferred method. Now proceeding with the latest trend of cloud, let's speak about AWS only. You will find the AMIs written for various operating system by which you just get a flavor of a particular operating system running in a cloud. So and obviously, on top of this operating system, the applications were running, the codes were deployed. So as of now, we know what were the preferred methods in different sites. Let's understand and discuss more about Docker images now. So it's nothing much for an operating system or for an application. It's just a read-only template, which consists of various instructions, where you simply means it can be a code, it can be libraries, the binaries or the tools that is required for your applications to run inside a container. So in short, it's just a read-only template of instructions that let you run your container in a Dockerized environment. So that was in brief about what is Docker image and how it works. Now let's see structure in detail. So it has a stack-like structure where it consists of one or more than one level of hierarchy. So it always starts with a base image or a parent image. So just for starters, a base image is nothing but a area where you build your own image from the scratch. While the parent images, you refer the image of someone else. Now you make some modifications or the amendments, run some commands, and an extra layer of images now added, or extra layer in images added. Now you run some extra commands and the file system now again incremented bit and you got a final layer of image. So in this complete image stack, you can find different level of hierarchies where the file system is differing in one or more aspects. Or in simple words, you can simply understand each layer is an increment over the previous layer. And obviously, these are all read-only images. You cannot write over them. So once this image is ready, you can spin off various containers out of that. Now, when a container starts writing anything, now that would be again a more read-write layer. Now you can use this read-write layer either to compile a new image for you, or in a simple words, if you destruct the container, that layer would be destroyed. But again, your image would be preserved as it is. So in simple words, you can simply understand this is a snapshot type of thing where I'm not sure how much comfortable with snapshots, but if you worked upon like storage snapshots or the backup strategies or the VMware snapshots, it's just like an increment over the previous stuff. So consider each layer as the increment over the previous layer. Each layer is not a complete operating system or a complete binary. It's not copying or duplicating the stuff. It's just adding an increment. So that is a bit about image in details. Now let's understand what benefit we got with this stack-like hierarchical approach in images. The first thing is reduce time to deploy. Obviously, it caches it. So the very first time when you run a container, maybe you don't have that image locally downloaded to your system. So Docker would connect to the Docker registry or any other private registry configured for your system, downloads that image and then spin a container out of that. Now, when you execute the second time, the same command to run another container, Docker is not going to refer to the registry. Instead, it finds in the local system cache, and you would notice a drastic amount of difference in the speed of a container build. Then obviously it has a lower storage footprint. So if this word looks confusing to you, let us stand with this example. For example, you have an image with 3 layers of stack and the lower one is the parent image. Now you try to pull one another container image, which obviously uses the base parent image, but the increment is a bit different. Maybe on a just CentOS image, one the downloaded you have the MySQL, the another you are downloading inside the Apache. So it's not going to download the complete base image again and the other layers again. It would only download the incremental part of the new image and bind it with your base image. So in this case, again, the duplicacy of the images are less. So that means you're actually using very less storage footprint for different type of images. The same parent image is now catering for the two applications. At a later point, they're obviously lightweight. The containers and the images are all obviously like they're not complete operating system images. They contain libraries, shared libraries, the binary codes, the thing that are required or that can create a pre-environment to run your container, but not a complete operating system ISO. And it will not make any sense if you run an operating system over an operating system. So that is the beauty of Docker and how the things work over here. I hope you find this section knowledgeful and it solved your purpose. So please test it and let us know with your feedbacks. Thank you and have a nice day.